Good morning, everyone. Welcome to the third session of this ReThinking NewSpace webinars. Today, we're here to talk about preserving the Earth observation data quality through in-orbit calibration. So our colleagues previously talked about how to get a good image, what's the data that's coming out of this image, and we are here today with Stefan, who I had the pleasure working with recently, and they're doing quite a lot on how to make sure that when the satellite is up there, that you have the right image, or at least you get a very sharp image. And so this is what we're going to talk about today, but maybe let's take a step back quickly to give a quick introduction. So I'm Pieter de Leijen, I'm the Manager Innovation Acceleration here at Verhaert, specifically for the space and startup incubation and acceleration programs. This means I have the ability working together with startups working on Earth observation data, helping them with their business case, and this is how I got to know Stefan.
Yes, Stefan. Hi Pieter. So I'm Stefan Adriaanse, working for VITO now approximately 20 years, I think, and from which the last 12 years I was more specializing or occupying myself with radiometric calibration. So we talk about calibration. This is in general calibration of data and instruments, but I'm really focused on radiometric calibration. Yeah, that's the main activity of the last 12 years now. Yeah, that's maybe.
Let's maybe dive into some of the things that you're currently working on.
Yes.
Yes.
Yeah, okay. Okay. Just first a bit step back. Indeed, as you said, Pieter. VITO remote sensing is in the past being involved in actually the entire value chain of remote sensing, meaning starting from the platform instrument, let's say the design, involvement in the design, involvement in the mission design, let's say, that you can define what type of mission you want to do. And so further down, launching, we have not been launching, but we were at least following that up. But mainly the data acquisition and storage, also processing. So we do a lot of near real-time processing for different missions. You can see on the right, for ProbaV is one of actually the most important, let's say, where we were on the value chain from the top to the bottom. But others, we work for Sentinel-3, Flex, Chime, Sentinel-2, as you can see. And mainly in the data processing section, we also do the data quality by calibration and validation. Calibration really means that you look at the parameters used to impose a sensor model to go from a digital number to a physical value. Yeah. And in most cases, this is, in our case actually, is radiance values. Validation is more when you get a product out of the system at the bottom, where there are end users, and before you say okay to the end user, this is our product, you check this with other references, let's say, and then you can say okay, this quality is fine, sorry. and then we go on. But today it's all about mainly calibration, let's say.
Yeah. And I see some missions and I see some names, but I definitely hear the ProbaV, which is very important for Belgium. It's a full Belgian satellite, making it obvious actually that VITO is quite involved. But I don't know some of the other missions. Can you?
So there are, most of them are connected to ESA. Yeah. Actually, all of them, I think, if I can see correctly. You have Sentinel-2, which is a big mission, actually with more satellites in orbit. This is really a higher resolution coverage, full coverage every day also, and also with more spectral bands. ProbaV was really focused on vegetation. Sentinel-2 is wider, let's say.
And so you're talking about more spectral bands. Are we within the hyperspectral or multispectral?
No, in the case of Sentinel-2, Sentinel-3, also ProbaV is multispectral, up to 10, 20 bands over the visual and SWIR. Vernier and SWIR areas, as we say it.
Maybe let's explain for the
Vernier is the visual near infrared, which actually what we see. And SWIR is already more deeper in the infrared, the longer wavelengths. Yeah, that's mainly mainly the purpose of having these wavelengths is also specific applications like detection of clouds, for example.
Yeah. Okay.
The Hyperscout and Flex and Chime, these are really the hyperspectral missions. They have, let's say, hundreds of bands, depends on the mission, of course. And they often, well, sometimes they are just like, in the case of Hyperscout, this was an IOD, a test bed, where they can see what they can do with this kind of data. Flex is really focused on one type of application, namely doing chlorophyll retrieval.
So green revegetation.
Yes, you have the ProbaV did, let's say, the bulk vegetation detection. With chlorophyll, you really go into the physical parameter of the vegetation more in detail. It's also very complex subject, I must say. I'm not a specialist on this. I'm more working on the calibration itself.
Yeah. Yes. So if we have time left, and if there are questions, always feel free to ask. But let's see at the end if we can go further to it. Yes, let's continue.
Okay, next slide then. So just, this is a slide I made. I was talking about radiometric calibration. In practice, what it means is that you use data that the satellite, the instrument, can see and can take. Yeah. You use that. These are always certain targets that they acquire, and you look and you take this specific kind of data, you take that to recalibrate your instrument. Mm-hmm. Yeah. For instance, in the case of ProbaV, we developed this really from scratch. We took in practice 10 different types of calibration, going from looking at dark oceans, over looking at a stable desert site, etc., etc. And I put here also the moon, which is also a nice target.
A bit elongated, but
yes, indeed. That's I left it on purpose like this because that's the way. This is an image of ProbaV. I think the blue band doesn't really matter, but the way the moon is scanned introduces this elongation. Okay. Because the speed of scanning, it's a line sensor. It scans line by line, and due to the speed, it oversamples the moon. It sees the moon more than one time, let's say. But that the moon is an example. That the bottom, let's say, blue.
On the left. Yeah,
on the left, exactly. This is really monitoring the stability of the radiometry. So radiometrically see if the instrument stays stable, and these are the x-axis is days. So you can see in years and years, it's only if degrading, let's say 2%, which is not a lot, which is very good.
Doing very well. And I see it's always on an intermittent point that you have a calibration, and then it always looks at the moon, or there are other targets that it sometimes.
Well, this plot is really for the moon only, but we verify this. Well, we combine these different methods, like for instance the desert. And this shows the same pattern. And of course, when you use multiple methods, you can verify. Is my method correct, or are they in conflict? And
was the data right? Because if indeed in the image you see somewhere around day 1100, you see suddenly a drop.
That's an outlier.
And that's an outlier.
And if the other method confirms this, then there is nothing. Nothing happened. This can always happen. At the right side, this is a nice example of this is geometry, checking geometry. The circle that you see in the middle. That's I think the resolution or the I'm not exactly sure. It can also be the requirement of the system, but it's in meters. Let's say 200 or 100 meters. At the left side, this is just when we applied the on-ground ICP. On-ground meaning as the instrument was measured on ground. Yeah. And in flight, we try to correct this by also just looking at data at the ground and comparing, matching this with existing data. Okay. And after this recalibration, you can see that we are nicely within this. I think the requirement was 100 meter. I think. Yeah. Of this. This requirement. Okay. So that's a bit what we did. We made a lot of. We took a lot of methods and we just put them together, and that was our way of working actually up until now. And it still is. It still is. If we see to the next slide, it's clear that we
that you keep combining this radiometric and...
Yes, indeed. So up till now we were tied to missions, a bit ad hoc based. We started with ProbaV, but as you saw, there were new missions coming up. But so often we saw that there were new players in the market, like often more commercial players, and they wanted some advice, or they wanted us sort of consultancy, but we could not really answer that because we were really focused on these projects, and everything was a bit organized in this way, which was very good because it's also needed for TESA.
And it had a clear statement of work. That's when we need it, and so it's very different from a commercial way.
Often you have to reply quickly and with quote very quickly, a quote, of course, and often we were not really prepared for that. So there was an idea of a colleague of mine to organize ourselves a bit better with, and we call it Calibrio now, calibration of Earth observation data, and really exploit calibration as a service. So the goal of this service would be improve the quality for everyone who wants their quality improved, let's say. That we have indeed a shorter startup time, or a response time, if you can call it like that, and also be able make sure that these customers can deliver consistent data, so also in time keep track if needed, and very specifically reduce the cost, thus by organizing ourselves better.
Because I don't think we have mentioned this before, but there are not many players with the experience currently on the market to really calibrate these optical instruments.
And let's say on a European scale there are a handful, let's say. On the world scale, 2-3 handfuls. Certainly the ones that are focused also, or better maybe, also looking at the commercial market, let's say, and that's the reason why we think this is a valid path to go. And also that's why we contacted you, also to be able to organize ourselves.
So to pretty much to have a third party opinion if this is really a business case. And I think if we go to the next slide, we actually do have an idea. If we try again. Oh no, this is actually a very good slide. It's like to showcase the different methods. A quick question to the audience. If there are questions, if we go too fast, please feel free to send your questions, and then we can take them at the end of the session.
Yes, indeed. So indeed, this is a good slide. I almost forgot we had it. But indeed, what it shows is how we were organized. We had a lot of methods, like geometry, radiometry, and all were a bit combined depending on the mission, and actually we could not. We really had to regroup everything. That was the goal in the future, to be able to what actually that's what you told us, but probably this is on the next slide, I would say. We have a next slide. But actually, I want to ask a question.
Yes, of course. Why do you make the distinction? Why do you have two geometry and two radiometry? Where you make the distinction?
This depends on the methods that have been used, but also the actual application. In this case, there is also on the left side more MTF. MTF is between radiometry and
What does MTF stand for? That's a good question.
I forgot.
But maybe it's more important. So what does it do? So
it defines how sharp your image is.
Okay. Yes.
So it really shows if your edges in your images are really sharp. Yes or no. I know the term because it also in this case we use the ground target, but also based on the moon you can do this this type of calibration.
Okay. And then on the right you spend a bit more. I think it's more focused on the bands and data acquisition points compared to each other.
So indeed we had a nice set of methods and combinations, but indeed we should have grouped.
It's the way of working, but indeed, so explaining this to a customer, of course, is nice, but it would take a lot of time. And then when you came with the question to us on where are we heading, is this really a business case? It was a pleasure for us to actually talk with some commercial providers. So we see, for instance, Imera Sense, Pixel, and now ScanWorld, I think, that we talked to. And there was a clear known challenge with these two distortions. So radiometric, they were fully aware, definitely in the hyperspectral, because bands are becoming closer and closer to each other, that this is really a challenge to figure out and requires some knowledge. Geometric was easier to solve, easier to fix, according to them. I don't know if you share that opinion as well.
Well, it depends. Probably my colleague won't. No, but indeed, it depends really on the difficulties that you encounter. In a normal scenario where you launch it and your instrument behaves very well, this counts for radiometry and geometry actually, then there is nothing.
There's no problem.
Then this is easy. You see easily what's happening, and then you actually don't have to do a lot probably. But when the issues came, for example with Proba V, there was a case that the star tracker had some issues. And this was not detected by the system, neither by engineering, let's say, on the side of the platform. But it was clearly seen in the data. And then we really, and after some combination with the platform builders, okay, then it was decided it is the star tracker. But I mean, it's can be very easy, but can also be very complex.
And so it's always nice to see like where is the problem. And the startups are well aware of this challenge, and we saw that there were two distinct ways of them approaching this problem, in the sense that some start building their own data pipelines very soon, while others are a lot more focused on let's get a satellite in orbit and let's at least see what can we get there. And it's two different ways, because the data pipelines often include already some experts. There are not many, but there are some experts that might join these startups and figure out this calibration. And so we came quite to a conclusion that, of course, startups are price sensitive. But some of our suggestions were to have like a clear pricing point, and also divide a bit. What can you do? You already mentioned like sometimes it's needed, sometimes it's not needed. So let's split up this service that you can provide. And I think actually the next slide already shows quite well on what's possible and how you address this.
So that was the let's say the main asset, or the main, let's say, conclusion of our exercise. We did a few rounds of discussions. One of the things that came up in the beginning was it's not going to be easy. I mean, it won't be just like, oh, the customers will be in line here waiting for you, like when you buy a bread or something. So, but okay, that's what we more or less expected also. But specifically, what you did by questioning these parties is identifying the fact that they really want some kind of shopping list. That's actually the name, I think.
We call it a menu, but
okay.
Indeed.
Okay.
It's
sorry.
It's indeed it's certain features that you want to know.
Indeed, and we went. Okay, we had ourselves focused a bit on that after this advice, because actually this is just the beginning. We are now going to develop this project, but we decided to really do entry-level quality verification. That's more. It's closer to validation, let's say. Less. Well, it's also calibration, but it's closer to validation. Let's put it like that. The center we do already express calibration.
And maybe let's say on the entry level, this is where you would define where if there is a problem or if there's not a problem with the data. Or
what would happen then is that a customer comes to us and asks, okay, I have now something an instrument in orbit, and we'd like to know if we are in, let's say, generally speaking, good, or good enough. And then with simple assessments, this can be done. And very short lead time, you call it maybe, or
lead time. Indeed.
Very short lead times. After 1 month, maybe 2 months, if we have enough data,
you have an answer. Yeah.
And then you can get a simple or a clear answer to that, indeed. And step further is on the middle is going a bit more complex. There we need probably also more time, and also, well, there is a short time, but it's always relative, of course. More time than the left one, less time than the right one, of course. But we look more specifically to certain parameters like dark current. Really, while the left one is more looking at the absolute radiometry, and then we're not going to dig into the detail. Let's say that's a bit like that. And then the right side is, let's say, is the full menu.
Yeah.
Then you do the
deluxe platter.
Yes, exactly.
And so it's full calibration, getting everything in line. And if you, what's the end result actually? We haven't discussed this.
Yes, indeed. And in all these cases, you get some kind of report.
Yeah.
Where you get an overview, and they say, okay, this is the level of accuracy. This is the level of radiometric stability, maybe. But at the right side, the right service level, let's say, you also get an update of your parameters, your system parameters, so that you can apply yourself new parameters so that we have really identified where you should tune your instrument.
Yeah, the system, exactly. The system where you can tune it, you'll give new parameters.
And then we get, so that it's a bit like that.
Yeah, okay, great. Thank you very much, Stefan. And that's actually, it's also, I think, our last slide, so we can go into some of the questions of the audience. So please feel free to send in our questions. And let's start with the first one.
Just a small drink.
Definitely. The first question that we received from the audience is actually, is calibration needed periodically, and would real-time calibration be of interest?
Periodically, yes, of course. Your instrument is degrading constantly. One instrument degrades faster and more than another. That's logic. So for the case of ProbaV, I can say that we updated the parameters I was mentioning before.
Yeah.
By the way, MTF is modulation transfer function. It got back to me. We every month they were updated, and certainly some parameters change really fast.
Yeah.
So this also answers a bit the second part of the question.
Part of the question. Okay.
Yes, this is actually also real time, because every day you acquire data, special data, calibration data, to do these updates. Yep.
Okay, very good. So it is an interest of people with constellations to do periodic. Talk to VITO. By all means, indeed, with some new research. But so let's go to the second question. So what about making calibration and autonomous tasks on board of the spacecraft? How far have we come to this?
I don't know missions that have this on board, except for, well, autonomous, no. Well, there are onboard devices often, like solar diffusers, they call it often. Or LED lamps that go before your instrument. And how far are we? Well, this really depends on the demand. I haven't seen a lot of missions doing that exactly. So I cannot really answer that.
Okay. I know of cases where they're introducing ASICs, so it's an edge AI computing on satellites, but I do believe that the power constraint is currently one of the big issues.
The platforms are getting smaller.
Yeah,
certainly the commercial players, they really go smaller and smaller. Logic, everything electronics
cheaper,
and cheaper. So often there is no means of putting devices on board.
Yeah.
Okay, you can say that you can recalibrate on board using the data that the instrument sees, but yeah. As mentioned before, it's still easier now to do this on ground.
Yeah.
It will come maybe, but for the moment I don't see it. Yeah.
So maybe let's make the assumption that it's currently more costly to include the calibration on board, like through launch and fuel and power, and that it's actually easier to do it on ground on the data that we get for the moment. All right. Third question, is Calibrio service going to become a spin-out?
That's a good question. Not to my knowledge.
Not to your knowledge? No, we actually had a discussion about this right before our session. Not today. I think it is important to know that VITO is a commercial organization and also a research organization.
Yes.
So not solely a research organization, and that's the reason why it's...
VITO has a history of spin-offing, so this is certainly a very good question. But let's say for the last 10 years we have developed the spin-offing, and also only really the last 6-7 years this has become more and more an automated process. So it's a possibility, but for the moment it's not on the table.
Yeah. Maybe when everybody's launching their own hyperspectral constellation, we'll see this coming up. Could you provide 3 concrete use cases that match these 3 calibration services?
Oh, that's difficult. Well, for instance, as I mentioned before, when you have launched, when let's say a satellite player or a commercial player has launched a satellite, he has his own full stack of methods in-house, but he really wants an external quick evaluation. Then this left, the light version, let's put it like that, comes into play. If he wants more also a timely, so let's say take half a year or a year stability, then this second option comes into the vision. So then you really are already looking at the degradation, for instance. So the first one is just a record. The second one is let's say a time of half a year, let's say. And then the right one really can be that the customer likes us to monitor the instrument
continuously
during its lifetime. During its lifetime.
And definitely most interesting at the beginning, like when you have a new satellite, the first of its kind up in orbit. I think the third one is also a good option.
Yeah, exactly.
Okay. I see we have one last question. Let's go through it quickly. I guess calibration offers of services is purely based on vicarious calibration methods. How do they compare to the accuracy with complex onboard calibration systems?
That's a very good question, and it's also a concern of especially ESA. Well, onboard devices often are, of course, better due to the fact that they are close to the instrument and that there is no well, let's say pollution in between what you're seeing and what you're recording. Well, for instance, like a solar diffuser, also this degrades as well. So, but accuracy, you can say that certainly, for instance, the moon calibration is going down in accuracy. Let's say it's improving, improving in accuracy, and it's coming more and more closer to what has been seen with solar diffusers. And if you say solar diffusers are 1% accurate, then these moon calibration claims to be 2 to 4% already. So. But this is evolving a lot still.
So keep an eye out, and this is it for our session. And we'll give the mics to our colleagues who are actually going to talk about, now you have the right image, what is the insights and the information that we can get out of it. Thank you very much.